move on with Zuhal Er. Can you hear me?
Hello.
We cannot hear you.
Is it okay now?
Yes,
Mubaş
so our paper presentation will be
together.
presented by the Mansur family. So
Okay.
I would like to give my utmost thanks to all of you. Floor is yours. Screen is yours. Sorry.
Thank you so much.
Thank you so much, dear Professor Zuhal. We highly appreciate the opportunity to work with you and to present our work here today. So without further ado, apparently I can't have screen sharing.
I give the permission. Now you can share it.
Okay, perfect.
Thank you. Thank you.
Theoretical analysis of oxygen vacancies as cause of gray shade in sintered aluminum oxide. Is it right?
Yes.
Okay.
Exactly.
We
Thank
are
you so
listening.
much. Perfect. Thank you so
So,
much.
hello again. It's a great pleasure to be presenting at the 8th International Conference on Computational and Experimental Science and Engineering. I am Mahia Mansour, and I'll be presenting our talk with my dear siblings, Mubashir and Maria. Our presentation is on the ab initio investigation of gray shade in as-sintered transparent alumina ceramics. Now, this work has been carried out at Istanbul Technical University through the collaboration of the Applied Physics and the Materials Engineering Department. The outline of our presentation is as shown here. We will go through the amazing properties of sapphire and alumina in general. Then we will discuss the elusive problem at hand, which is an undesirable grayish shade in as-sintered alumina, followed by our computational methodology to tackle a theory on the cause of this issue. And finally, we will refute a theory based on our calculations. Towards the end, we will weigh in on the other possibilities, which are more likely the cause of this problem.
So let's begin with a quick overview of the amazing properties of aluminum oxide. The single crystal form of alumina is a very well-known material, sapphire. It has been used as a gemstone for perhaps millennia. But this is so much more than a gemstone. The amazing hardness of 22 gigapascals, melting temperature of 2050 Celsius, resistance to many corrosive media, wide transparency range from 200 to 4,000 nanometers makes it an amazing material for all sorts of demanding applications. However, producing single crystal alumina or sapphire is not an easy task. So an alternative which can provide almost all the industrial benefits of sapphire is actually polycrystalline transparent alumina ceramics. Now, it is possible to sinter alumina powder to complete transparency under pressure using state-of-the-art methods such as spark plasma sintering.
But there is a problem. The as-sintered alumina ceramics turn out to be grayish for some unknown reason. There are a number of possible theories when we look at the literature, the most important of which are oxygen vacancies, carbon diffusion, carbon precipitates, and impurities. Some researchers have attributed this shade to oxygen vacancies because if you look at the SPS equipment where sintering is taking place, there are many graphite components and the atmospheric conditions are inevitably oxygen poor due to the Baudouard reaction. Based on the defect thermodynamics of alumina, oxygen vacancies are a dominant defect under such a reducing atmosphere as seen here. And since subsequent heat treatments of such ceramics under high oxygen partial pressure can make the ceramics colorless, it has led to many to consider oxygen vacancy as one of the primary causes of this gray shade. So the optical behavior of this point defect requires a very careful investigation. Here is a typical absorption spectra of such ceramics. There is a continuous absorption across all the wavelengths in a balanced manner, which causes the gray shade. So we embarked on a journey to calculate the absorption spectra, which should be expected from oxygen vacancy defects, to see if this experimental spectra can be produced by the theoretical studies on vacancies. If it's not possible to reproduce a similar continuum across UV visible spectrum through ab initio calculations,
then we can safely refute the oxygen vacancy theory as being the cause of the gray shade.
So we applied spin polarized density functional theory with the projector augmented wave method as implemented in WASP. And we have calculated the dielectric function by using the modified Beck-Johnson local density approximation as our meta-GGA exchange functional. Here's a band structure of the pure and perfect alumina cell without any defects, with the valence band of the p orbitals and a conduction band minimum at the gamma point made of the s orbitals. The idea is to see what are the defect levels induced by oxygen vacancy. Once we know the dielectric function, then we can use the complex part to calculate the absorption spectrum.
Now, here are the results for the single oxygen vacancy. There is a p orbital induced deep band, which is seen here in the density of states and band structure plots. When we consider the absorption spectra, it is unlikely for this defect to have an absorption in the visible spectrum based on the MBJ LDA exchange functional. But one should expect absorption peaks in the short wave ultraviolet. It is also interesting that the energy of the defect level is almost independent of the K point.
Now, this is very important because since the energy level is independent of the K points, it gives us the opportunity to do similar calculations in the future with much less computational cost. So that's an important thing to remember. And here is the calculated absorption spectra as we would expect, shown here.
Exactly. So when we look into an extended vacancy defect or a die vacancy, the spectra is different because of the three allowed states in the band structure. We do have a red shift of the absorption edge in our calculated UV visible spectra, but the absorption is still in the ultraviolet region, this time in long wave UV. There is also a difference in the UV absorption with respect to crystallographic axis.
Now, this is kind of expected since sapphire or alumina is anisotropic.
Yeah.
So it's interesting to see that there are two different peaks occurring with respect to orientation, so in the X or Y or the Z direction.
But again, there is no continuum in this case either. So we cannot expect a grayish color from the die vacancy defect as well. So we can now safely say that oxygen vacancy and die vacancy are not capable of creating a gray shade in alumina. And we can refute the oxygen vacancy theory based on this research.
However, the question remains, if oxygen vacancy is not the cause here, what else could it be? Now, we would like to bring your attention to the alumina boostite phase diagram. Iron oxide has a very high solubility in alumina under most conditions, and under the majority of powder synthesis routes, even up to 5,000 parts per million of iron can get dissolved into alumina if there is enough iron contamination available during the powder synthesis process. So this high solubility turns out to be very much oxygen dependent, as we see in our fact stage calculation. So what happens is, as soon as oxygen partial pressure drops, precipitation of iron occurs. Now, even if there is only 10 parts per million available, when we consider the usual oxygen partial pressures during SPS sintering, this is inevitable. Now, this would also explain why these ceramics become colorless and fully transparent through subsequent heat treatments and oxygen-rich atmospheres, because then you would be actually redissolving that precipitated iron back into the alumina crystal. So this is a very good hunch to maybe start another journey or another hypothesis to go on to.
So here is a remarkable paper by Professor Moon. They have witnessed this phenomena during a heat treatment of iron-bearing natural sapphire under extremely low oxygen partial pressures. Once these iron crystals precipitate, they will surely result in scattering and an absorption continuum which shifts the ceramics towards gray and ultimately black appearance. So we highly recommend further studies of such gray ceramics under high-resolution transmission electron microscopy in order to learn more about the secondary phases, which are capable of causing such a gray shade.
Because we seem to be pretty sure that oxygen vacancies like point defects are not the cause here. So to conclude, just a quick recap. The problem that we tackled was to find if oxygen vacancy can cause a gray shade in as-sintered alumina ceramics. We applied spin polarized density functional theory to calculate the band structure and optical response function of the oxygen vacancy and dye vacancy defects. And we found out that these defects are definitely not a possible cause for the gray shade. And also, we anticipate that secondary phases, such as iron, are a much more likely cause, which makes it very crucial to study these ceramics under high resolution TEM to be absolutely sure of what's going on.
We would like to thank our dear advisors, Professor Zohal Er and Professor Filiz Çınar Şahin, for their great support and encouragement. We are also thankful for the supercomputer support of the National Center for High Performance Computing, UHEM, here at Istanbul Technical University, and their grant which made this research possible. We look forward to any questions and comments you may have. Thank you so much for listening.
Thank you.
Thank you.
Thank you for your really nice presentation. I really enjoy it. Even if I am far from the subject, it was really nice for me. Thank you.
Thank you so much.
We highly appreciate it. Thank you so much.
Is there any question about the presentation, please? We are waiting for the questions.
Well, if there is no scientific question, and I also congratulate, I thought that this is the news presenter or something on the TV. That's very nice.
Thank you. Thank you so much. We do our best to put all of our energy into the presentation. I think science of it is some percentage of it, but the way it is presented is maybe sometimes more important. So we do our best.
We try.
That's very nice.
We try.
Thank you and congratulations.
Thank you once again. Thank you.
Thank you. We feel your energy, really.
You're very kind. Thank you.
Thank you again.
Once again, thank you for the great organization. We really appreciate it, and we hope that in future we can actually visit your conference in person and participate.
Next year, we hope. We are waiting you.
Hopefully.
Antalya is great. We look forward to it.
If we do it face to face, we are expecting to same type of presentation. 3 people.
Oh, absolutely.
Yes, perfect. Yes.
Thank you so much. Thank
Thank you
you.
so much.
Thank you. See you.